So, we are going to get started with force video number 2. Okay, and this deals with the inclined plane at a 30-degree angle. And one thing that I'm going to do to start off is I'm just going to flip the axes and call them downwards to the left, the positive x-axis, just so that we can simplify all of our values and our angles. Okay? Alright, first step we have to do is draw the forces acting on the mass. Well, the mass has a force of gravity that is going to be straight down. And then perpendicular to the contact surface, we will have a normal force, which is upwards but at an angle. And then if you remember from our previous video, we can go ahead and extrapolate a line back here and make our little right triangle with a 30-degree inside here. And this will show us that we have a force of gravity down the slope. And the force of gravity down the slope is actually seen acting right in the middle here. Alright, so now we have labeled the forces. In the first case we are going to be doing with no friction, so we don't have to add friction to this problem. And so we have included all the forces in blue vectors here. And so now the next step is to write an F-net diagram. Sorry, F-net equation. So we write F-net in the x direction is equal to, and we're only going to do this one force that is acting in the positive x direction, and that will be the force of gravity down the slope. Now we go ahead and do our expansion step. F net x always expands to max, while the force of gravity down the slope will expand to mg sine theta. And now the masses cancel out, and your acceleration in the x direction is g sine theta, which is approximately 5 meters per second squared, because the sine of 30 is 1/2. Okay? So that is one way. And again, what we really need you to be able to do is write this top statement here. Everything else just becomes simple algebraic substitution after that. Now let's do a case where we have friction added. Okay? In this case, the coefficient of friction is going to be 0.5. And in that case, I have to add the force of friction vector acting on the box here. And that vector is going to be acting up the ramp, or in the negative x direction. And so when I write out my F net equation, it's going to look like this. F net x is equal to the force of gravity down the slope minus the force of friction. Okay? Again, these are vector quantities, so I have to do the appropriate either addition or subtraction based on the direction of that force. And that's why it's so important to draw out a proper force diagram, because it's linear. Once you get a proper force diagram, it'll lead you to getting a proper F-net equation, and that will lead you to the right answer. So now I'm going to do another expansion step here, and F-net x is going to expand to max, like always. And the force of gravity down the slope is going to be mg sine theta. And the force of friction is going to be mu times mg cos theta. I can cancel out all my masses now, and I'm left with acceleration equals g sine theta minus mu times g cosine theta. And the sine of theta is about 0.5, so that gives me 10 times 0.5 minus, and then mu is 0.5, so 0.5 times 10 times about 0.87 for the cosine of 30. And so that gives me about 5 minus 4, which is going to give me an acceleration of 1 meter per second squared. Okay, so what we should recognize here is that the acceleration did decrease when we added friction, which is what we expected. And again, the most important step here is that you are able to write the F-net equation, the force of gravity down the slope minus the force of friction. If you can successfully write a good force diagram, it's only a matter of time before you will keep getting the right answer. Keep practicing this technique. If you have any questions, consult your tutor. See you soon.